When electricity is passed through a conductor, it displays a magnetic effect. This effect is responsible for the magic you just witnessed. In this lesson, you will learn about the magnetic effect of electricity. At the end of this lesson, you will be able to describe the magnetic effect of electricity. Apply Maxwell's right-hand grip rule and Maxwell's corkscrew rule to locate the direction of magnetic field lines due to current carrying conductor. List the properties of a magnetic field and field lines around a straight conductor, a circular coil, and a solenoid carrying current. Analyze an electromagnet. Apply Fleming's left-hand rule to find out the direction of force on a current-carrying conductor in a magnetic field. And demonstrate the construction and working of an electric motor. Hans Christian Ørsted conducted an experiment to demonstrate that electricity produces a magnetic effect. The experiment is set up for you, as you can see. Let's see what happens if we close the key to allow current to pass from south to north. The magnetic needle originally points north. However, when current passes through the wire from the south to the north, the needle deflects to the west. As you saw in Ørsted's experiment, when an electric current passes through a conductor, a magnetic field is created around the conductor. This phenomenon is called as the magnetic effect of electricity. Let's analyze this magnetic effect further. You will observe that if you place the compass above the wire and allow current to pass from the south to the north, the compass needle deflects to the east. If you reverse the direction of the current in the wire, the direction of the deflection of the magnetic needle is reversed. The angle of deflection is directly proportional to the strength of the current through the wire. A magnetic field is the extent of space surrounding a magnet where the magnet's effect can be felt. Thus, it represents the region under the influence of the magnet, just as an electric field represents the region of electric influence. A magnetic field consists of a number of magnetic field lines, generally referred to as magnetic lines of force. Magnetic field lines represent the lines of action of the force acting on a unit north pole placed in the magnetic field. Magnetic field lines are closed continuous curves, never intersect each other, mutually repel each other, travel from the north to the south outside the magnet, and travel from the south to the north within the magnet. You can determine the direction of magnetic field lines due to a current-carrying conductor using Maxwell's right-hand grip rule. According to this rule, if you hold a conductor in your right hand with your fingers curled around it and your thumb stretched out as shown, then your thumb denotes the direction of the current in the conductor, and the direction of the curling of your fingers indicates the direction of the magnetic field lines due to the conductor. In the example shown, the current in the wire AB passes in the direction of the thumb, from end A to end B. The direction of the magnetic field due to the current in the wire is represented by the curl of the fingers, as shown. This rule is also called Maxwell's corkscrew rule. Consider a right-handed corkscrew kept parallel to a current-carrying conductor. On turning, if the screw advances in the direction of the current, then the direction of rotation of its head gives the direction of the magnetic field lines due to the conductor. Thus, magnetic field lines around a current-carrying conductor are in the form of concentric circles and can be either clockwise or counterclockwise depending on the direction of the current. Magnetic field lines vary with the shape and form of the conductor. Let's take a look at the magnetic field and field lines around a straight conductor, a circular loop, and a solenoid. An experiment will help you understand how magnetic field is spread around a straight current-carrying conductor. To begin the experiment, we fix a white sheet on a cardboard, which is clamped to a stand. Next, we pass a thick copper wire connected to a battery and key through a hole at the center of the cardboard. Finally, some iron filings are sprinkled on the board and current is allowed to pass through the wire by switching the key on. You will observe that when the current flows through the wire, the iron filings arrange themselves in a concentric circular pattern. By placing a magnetic compass on any circular field line represented by the iron filings, you can also detect the direction of the magnetic field lines. The direction of the compass needle indicates the direction of the magnetic field. Further, if you change the direction of the current in the wire, you will observe that the direction of the compass needle is reversed. Thus, based on this experiment, you can conclude that a magnetic field around a straight current-carrying conductor consists of concentric circular field lines. The direction of the magnetic field lines depends on the direction of the current in the conductor. In general, magnetic field lines around the straight current-carrying conductor form concentric circles around every point on the conductor, with the center on the axis of the conductor. Lie in a plane that is perpendicular to the length of the conductor. Increase or decrease with an increase or decrease in the strength of the current respectively. Create a cylindrical magnetic field around the conductor. We can analyze the magnetic field of a current-carrying circular loop through another experiment. We begin by fixing a white sheet on a cardboard and clamping it on a stand. Next, we pass a thick copper wire through two holes on the cardboard so that it makes a curve and forms the shape of a loop. Then, we connect the ends of the loop to a battery and a key. Finally, we sprinkle some iron filings on the board and allow current to pass through the loop. When current passes through the loop, the iron filings arrange themselves in two sets of concentric circles on the cardboard. Further, if you place two compasses on each set of concentric circles, you will notice that the needles point in opposite directions. This shows that the magnetic field due to a current-carrying circular loop takes the form of two oppositely directed sets of concentric circles. Magnetic field lines around a current-carrying circular loop have the following properties. The lines are circular near the loop and tend to get elliptical away from it. They travel in the same direction within the area enclosed by the loop. They are parallel to each other near the center of the loop, indicating the uniformity of the magnetic field. They lie in a plane perpendicular to the plane of the loop at its center. They increase or decrease with an increase or decrease in the strength of the current respectively. These lines create a south pole at the face of the loop where the field lines enter the loop, and the current in the loop is in a clockwise direction. They create a north pole at the opposite face of the loop, where the field lines leave the loop, and the current in the loop is in a counterclockwise direction. A solenoid consists of an insulated conducting wire wound on a cylindrical tube made of plastic or cardboard. Thus, a solenoid consists of a number of circular loops. That is, it constitutes a coil. The length of a solenoid is greater than its diameter. When current passes through a solenoid, each loop in the solenoid behaves like a tiny bar magnet, with the south pole of one loop facing the north pole of its adjacent loop, and vice versa. Thus, a solenoid consists of a number of tiny magnets of equal strength. All the tiny magnets in the solenoid together behave like a bar magnet. The end of the coil, at which the current in the coil is in a clockwise direction, develops south polarity, while the other end, where the current in the coil is in a counterclockwise direction, develops north polarity. To analyze the magnetic field and field lines due to a current-carrying solenoid, here is an experiment. In this experiment, we fix a solenoid in a slit in a cardboard. We connect this solenoid to a battery and a key. Finally, we sprinkle iron filings on the cardboard and close the key to complete the circuit. When current passes through the solenoid, the iron filings arrange themselves in a pattern that represents the magnetic field lines due to the solenoid. These lines can be traced using compass needles. Magnetic field lines due to a solenoid are parallel to each other and to the axis of the solenoid within it, travel from the south pole to the north pole within the magnet, and travel from the north pole to the south pole outside the magnet. The density of magnetic field lines indicates the intensity of a magnetic field measured in Newton per ampere meter or Tesla. The intensity of a magnetic field can be increased by increasing the strength of the current, increasing the number of turns in the solenoid, or inserting a soft iron core in the solenoid. Using electric current, you can create magnets out of metals like iron, nickel, and cobalt. Magnets created using electric current are called electromagnets. An electromagnet is a magnet made of a coil of insulated wire wound around a soft iron core. The iron core is magnetized when an electric current passes through the wire. In other words, an electromagnet is a solenoid with an iron core. Electromagnets are more useful than permanent bar magnet in the following ways. Electromagnets have a stronger magnetic field than permanent bar magnets. It is possible to reverse the polarity of electromagnets, but not in the case of permanent magnets. Electromagnets can be easily demagnetized by interrupting the current. However, it is difficult to demagnetize permanent magnets. In electromagnets, the intensity of the magnetic field can be easily varied. However, magnetic fields of permanent magnets are of fixed intensity. You can convert an electromagnet into a permanent magnet by using a steel core. A magnetic field exerts a force on the magnetic objects under its influence. Therefore, a current-carrying conductor kept in a uniform magnetic field experiences a force that tends to drive it away from the field. The direction of the force on a current-carrying conductor in a magnetic field can be determined using Fleming's left-hand rule. To understand this rule, stretch the forefinger, middle finger and the thumb of your left hand, holding them at right angles to each other. If the forefinger gives the direction of the external magnetic field and the middle finger points in the direction of the current in the conductor, then the thumb gives the direction of the force on the conductor. An electric motor converts electrical energy into mechanical energy using the magnetic effect of electricity. You find electric motors in household appliances such as fans, refrigerators, washing machines, pool pumps, and floor vacuums. An electric motor is built on the principle that a current-carrying coil rotates when kept in a strong magnetic field as it experiences torque. An electric motor consists of 6 main parts. An armature that consists of laminated sheets of soft iron, through which passes a shaft. A coil, in the form of an insulated copper wire looped over the armature. A magnet that produces a strong and uniform magnetic field. A commutator, which is a metal ring split into two and is also referred to as split rings. This commutator is connected to the two ends of the coil. The shaft passes through the center of the commutator. 2 carbon brushes tightly fixed to the 2 split rings connecting them electrically to the coil. A battery that provides electrical energy to the motor. Let's examine how an electric motor works. Consider a rectangular coil PQRS placed horizontally between the north and south poles of a magnet and connected to a battery. The end of PQ part of the coil is connected to the battery through the split ring S1 and the brush B1. The end of RS part of the coil is connected to the battery through the split ring S2 and the brush B2. Initially, current is directed from P to Q in the arm PQ and from R to S in the arm RS. This arrangement is similar to that of a current-carrying conductor in a magnetic field. According to Fleming's left-hand rule, the force on PQ acts in an upward direction and on RS in a downward direction, forming a couple. The coil begins to rotate until its plane becomes vertical, that is, perpendicular to the direction of the magnetic field. Magnetic fields of the coil and the magnets become parallel to each other as the coil rotates by 90 degrees and the couple acting on the coil becomes 0. However, the coil rotates further through 180 degrees due to inertia. The plane of the coil becomes horizontal again. When the coil rotates by 180 degrees, the split rings also rotate along with the coil. Now, the split ring S1 connects end PQ of the coil to carbon brush B2. Similarly, S2 connects RS to B1. This reverses the current through the coil. The current now enters the coil through S2, passes along S, R, Q, P, and leaves the coil through S1. The torque acting on the coil causes PQ to go down and RS to go up. The torque acts on the coil until it rotates through 90 degrees. Further, it rotates through another 90 degrees due to inertia and becomes horizontal again. On completing one full rotation, the split ring S1 connects PQ once again to carbon brush B1. Similarly, S2 connects RS to B2. Thus, as long as the coil is connected to a battery, it continues to rotate and convert electrical energy into mechanical energy. The power of an electric motor depends on the strength of the current through the coil, the number of turns in the coil, the area of cross-section of the coil, the strength of the magnetic field, and the lamination of the iron core. This lamination reduces energy losses.